Hey there, Math 2403. Welcome back. Continuing on with unit number 1. We're on to video number 3, measures of variation. We'll talk about range, standard deviation, coefficient of variation, and ways to interpret these values using the empirical rule and good old Chebyshev's theorem. Last time we were talking about measures of middle. Now we're moving on to statistical measures of spread. So let's get right to it. Okay, so some measures of variation. The first one is one you're probably very well aware of. That's the range. Oftentimes we use the word range to mean from A to B is a range of values. In statistics, it's a single measurement. It's the maximum minus the minimum. So it's basically the distance of the way you may have used range in the past. It's a nice measure of variation because it's super easy to calculate, but its downside is it is susceptible to outliers. So one strange value in your data set will make the data set look like it's very spread out even when it's not. You know, a quick little example, if I had a data set like this, you know, most of my values are pretty tightly grouped together here, but that one strange value there would really affect the range. The range of this data set is 100 or 1,000 minus 1, so 9999, which makes, sorry, 999, 999. So that gives you the impression that these values are really spread out all over the place, but in reality, they're all fairly grouped together. So the range isn't necessarily the best way, but it sure is a nice, quick, and easy way to measure. And if you don't have any, crazy values like this, then it is a decent way to measure how varied your data is. The next one is standard deviation. You've probably heard of it as well. We'll have one symbol for sample standard deviation. So we'll use S when we're talking about samples, and we'll use the Greek letter S when we're talking about populations. So that's a sigma. We'll use S to estimate sigma. We don't know the population value typically. We usually have sample data, and we will use S then as a measure of how varied the whole population is, even if we don't know what the population is. One thing to note here is that unlike the mean, the formulas for standard deviation are actually different depending on which situation you're in. So you have to make sure that before you just start calculating these things, you have to make your determination of whether or not you're working with a sample or a population. And that basically comes from the context of what you're working with. A quick example might be our class. You all wrote an assignment last week, and I may want to determine the standard deviation. How varied are the scores on last week's assignment? Now, I could view my class as the entire population. I could maybe call you guys a population, and then I would use this formula. But generally, because I teach this course over and over from year to year, and I often, maybe I reuse some assignments, you're basically a sample of all the students I'm ever going to have. So usually when I'm calculating the standard deviation, even in that context, I would view you as a sample of all the students I'm going to have in this course, rather than as the population of all the students I'm ever going to have. So you can see that basically every group you could basically call a sample or a population, depending on how you're viewing it. So make sure you check out the context of your question when you're making these decisions. Because it does matter. You get a different value. It's not just that you use a different symbol. The calculations are different. When we're looking at the standard deviation, you'll notice there's n minus 1 in the sample version, and there's n in the population version. Basically, this is a way to bias it. When you divide by a smaller number, you end up with a larger number. So by dividing by 1 less, we're actually inflating this value a little bit. And the reason we do that is, well, one reason we might do that is to err on the high side. Typically, we're using S to estimate sigma. And if I'm going to make a mistake one way or the other, I would rather err on the high side. I'd rather think that there's more variability in my data than there's less. The desirable property is to have less variation, typically. If your data isn't very varied, it's easier to make predictions. If I told you on the assignment last week, everyone got 10 except a couple people got 9, and you don't know what your score is yet, you feel pretty comfortable knowing that you got a 10. You can predict that fairly well. But if the scores are all over the place, the scores, there were a few 1s, a few 2s, a few 5s, a few 8s, etc., then it's hard to predict. So we like to have standard deviations that are smaller to make things more predictable. So if we're going to make a mistake, we err on the high side. That's what that n minus 1 is doing. And it doesn't really matter much if you have a big group. Like if I'm studying 5,000 values, subtracting 1 doesn't change the result very much. But if I'm studying 12 values, then this will start to factor in more. So I just wanted to mention that as some reason why that is kind of adjusted that way. I haven't even said what standard deviation really is, other than it's a measure of spread. It's basically the average distance of your scores from their mean. Maybe it would be helpful to do a little example, and then maybe that will make more sense. So suppose a family has 5 children, and their ages are 1, 2, 3, 5, and 9. I want to determine the standard deviation for this family, for the ages of the children. I plotted the kids' ages on the number line, 1, 2, 3, 5, and 9. I'm going to calculate the average age or mean age of these children. Now I have to decide, is this a population or is this a sample? I think in this situation, it says a family. So that's basically the whole population of that family. So I feel okay about using mu in this case. But you can see it's kind of a bit of a decision to make, and it will make a fairly big impact on your standard deviation when you only have 5 values. So it is an important one, but I think in this case, I feel comfortable calling this mu. So if I'm calculating the mean of those, children, the kid ages, I'm just going to add up all their ages and divide by however many children there are. So it's 1 plus 2 plus 3 plus 5 plus 9. Wow, can you imagine having a 1, 2, and 3-year-old? So many diapers. Divide that by 5. So we calculate this out. I picked nice numbers there for these kids' ages. It's 20 divided by 5. So on average, a kid is 4 years old in that family. And I plotted that on the number line here as this dotted line. Now, what is standard deviation? It's basically the average distance that any of the values is away from that mean. So I've put in the distances here. Like the 1-year-old is 3 units away from the mean. And the 2-year-old is 2 units away from the mean. And the 3-year-old is 1 unit away. And the 5-year-old is 1 unit away. And the 9-year-old is 5 units away. So these are the distances away from the mean. And I want the average of those distances. That's what standard deviation is. So even though I didn't memorize that formula on the previous page, the distance, like to calculate the length of one of these lines, I'd take the value x, on this axis, these values are all x's, and I'd subtract the mean. So it's x minus the mean is a distance. But I'm doing it for all of the kids, so I'm going to add those up. I probably should have, maybe I should be more, I've been kind of lazy about my summation notation here. Maybe I should write this as the sum as I goes from 1 up to 5 kids. Each children's age minus the mean of all the children. That's the distance. Each one of these is a distance. And if I add those all up and then divide by however many there are, I get the average distance away from the mean. But something weird happens. If you take a look at this, I took each of these distances and I translated them down to this number line, and some of them are negative. The 1-year-old was 3 units below the mean. So if I calculate that distance, I get -3, and this one is -2, and this one is -1. And I plotted those distances here. And then the positive ones, I have the 5-year-old is positive, and the 9-year-old distance is positive. Well, if I add all those distances together, the length of the green equals the length of the blue, and the green is negative and the blue is positive, so they'd cancel out and I get 0. So one way to fix it would be to actually do it in terms of, absolute distance rather than, so we wouldn't have to worry about the signs. But what statisticians have done instead is looked at, they made them positive by squaring the distances. It's easier to work with squared values than having to deal with absolute value. And then to correct that they've squared all the distances, we take the square root. So that's our formula for standard deviation. It's rather tedious to do. These numbers are nice, though. I'm going to do each of the distances. So the first x was the 1-year-old. So I have a 1-year-old minus the mean, which was 4 years. And then we square. And then we're going to add that to the squared distance of the 2-year-old. So that'll be 2 minus 4 squared. And then the 3-year-old. You can see you probably don't want to do this for 50 values. This is where Excel starts to help us out, I guess. And then the 9-year-old. And we're dividing that by the 5 kids. And then don't forget the square root. So the numbers I picked here are pretty easy. But the square root I still need to take out my calculator. Even though I rigged this thing, 3 squared is 9, 4, 1, 1, and 25. I'm still going to have to dig my calculator out in order to get this square root. It's the square root of, what is that, 40 on the top? 10, 15, 40. Well, it's a nice number, though. It's the square root of 8, but I don't have that one memorized. So take out my trusty calculator. I have the same calculator that you guys have. It's just a virtual one. So how do we do this? Square root of 8. Oh, it doesn't give it to me. What kind of mode do I need to get that into? Not that one. Oh, I bet it's this change, huh? Aha. So, you guys are probably better with your calculator than I am. So it's 2.82, or the average distance away is, 2.8 years, which is fairly spread out. If you put these 5 kids in a, dark room and you randomly selected one, how old do you think it's going to be? Well, you'd probably guess it's around 4 years old, because that's the average, even though none of the kids are 4. And it's hard to predict how old they are because the standard deviation is 3 years. The average distance away from 4 years is almost 3 years. So there's a pretty wide range of possibilities, which makes this hard to pick. So had this number been much lower, like 0.5 years with a mean of 4 years, then I have a much better shot at guessing the age of a kid in a dark room. That seems kind of weird, doesn't it? That's a bad example. But anyway, if the standard deviation is small, it's a lot easier to make predictions. So smaller, the better. Although you can't really control it. It is what it is. So this is a hard prediction to make. So the larger it is, the harder it is to make predictions. While we're at this calculation point, I don't think you ever want to do this by hand. Calculating standard deviation is terrible. And this one was easy because we had all integers, but imagine if these were all decimals, and imagine if we had more values. You can put your calculator actually into a stat mode. It's currently a normal mode, but if you choose mode, you may not have noticed, but you have a stat mode, so mode 1. And then it gives you various stat modes, and they're kind of weirdly named. The first one is SD, then line, quad, exponential. We want to be in SD. It stands for single data set. So I'm going to press 0 next, because I have a single set of data. And that's mostly what we'll use in this course. Now that I have the calculator in stat mode, I want to enter these 5 values. And my calculator will then just spit out the mean and standard deviation. It's pretty cool. To enter them, you just go one by one. So I have a value, I have a 1-year-old, and then you hit this button here that says data. And now my data set shows that there's 1 value in it. And then I hit 2, and then data. And now my data set has 2 values. 3, data. The next kid was 5, data. And then the last kid was 9, data. Everyone forgets to hit the data button on the last one. So it shows that I have 5 values in my set. If I want to now calculate the mean, if you look above the buttons, you see that there's green. I think on your calculator, they're also green, or a bluish green. You'll see that above the 4, there's an X bar button. So that's your mean. And I know there's no mu button on your calculator, but that's because the formula is the same, whether it's mu or X bar. So we can just use that. And to get to the green buttons, you use alpha. It's also green. So you say alpha 4. And now I'll have to hit equal to have it calculated. And ta-da, we get the 4 years. So that's pretty cool. To get the standard deviation, I don't have to punch the numbers in again. They're still stored in there. So even if I hit clear, they're in there. You know, if I say alpha 4, back to, it gives me the mean. So if I want the standard deviation, you look above the buttons. And if you look above the 6, it's sigma. Sigma for x values. You'll notice that there's a sigma y as well. Later, we'll learn about another mode where you get to enter values in pairs, where you have x's and y's. And you could calculate the standard deviation of the x's and the standard deviation of the y's. But for now, we're just dealing with x. So basically this row, 4, 5, and 6 are our important buttons. So alpha 6 will give us our population standard deviation. Alpha 6, and it gives you this weird sigma with a subscript x. And hit equal, and there it is, 2.8 years. If this data had been sample, suppose the family had, 14 children, but we only picked 5. Then this would be a sample, and I would say alpha 5, because that gives me the sample standard deviation. And that's probably the one we're going to use more often anyway. And you'll see that it's larger. I said that S tends to overestimate sigma. And I was correct in this case, especially when you have small data sets. You have a tutorial on this that you get to work on in your lab. So if you're not, following along with this, that's okay. You'll get another chance. But this is a nice video of it, I guess. Oh, one other thing to point out is that you can actually scroll through and look at your values. So see your arrow buttons here? If you click on them, it'll say data set 5. The 5th value in my data set was the number 9, and I have one of them. That's what F is for frequency. And you can scroll through. If I scroll down, the first value in the data set was a 1. I guess I keep hitting down. The second value is 2. So you can check to see if you entered them correctly. And if you made a mistake, suppose, your 4th value, it wasn't a 5-year-old. Suppose that was supposed to be a 6-year-old. I could hit 6 right now, and then I have to hit the data button to get it to store it that way. So now I'll have a different mean. If I say alpha 4, oh shoot, I gotta get out of there. If I say alpha 4, now the mean is higher because I made one of the values higher. So it totally makes sense. The last thing you need to know how to do is, it doesn't seem to go away, right? If you have new data and you want to start over, you hit second, and then you want to clear all. So above the mode button is CA. And now the data is gone. Like if I try to hit the arrow buttons, there's no values in there. The other way to clear it out is to go back to normal mode. You can go mode, normal, and now that data that was in there gets wiped out. So yeah, that's the secrets of the calculator. Of course, I think it's easier to use Excel, but you may not always have Excel with you. So suppose we wanted to do this again, using Excel. There are a few different ways of doing this. I'll try to blow this up so you can see. My kids' ages were 1, 2, 3, 5, and 9. And I want to calculate the mean. So I'm going to just, put a label here, and I'm going to put the mean in this cell. To do that, I wish the function were mean, but that isn't a function in Excel. They goofed up and they called it average. So I'm going to say it's average, and I want to find the average of what is in cell B3 colon B7, and that highlights the whole range. So if you're using your keyboard to enter this, B3 colon B7. Another option is to use your mouse. Like once you start the function, you can just highlight what you want to find the average of. And that's probably safer because you won't mess up. Like you can actually see what it's highlighting. But I don't like to have to dig out my mouse all the time. And hit enter, and we should get 4. So maybe put some units next to it. And if we want the sample standard deviation, which we didn't want, but suppose we did. I'm just, giving you the Excel demo here. If you double click between two columns, it will resize them to the biggest item in the column. So if I do that, you can see it resized it to this. And then in this cell, I can calculate standard deviation. I just start typing. I'm not sure what the function is. I must start with S, T. Oh, look at it, suggesting things. So STDEV sounds good to me. We are trying to decide if it's a sample or a population, and I'm choosing the S because I'm calculating S here, the sample standard deviation S. So STDEV dot S. And it even gives you a little description of how it works. And then again, I want to do B3 to B7. And then we wanted the population standard deviation. Can't spell. I want that to be a sigma. So what you can do is, I'll resize that. What I do to convert that to Greek is I just highlight the letter, and then I cheat and I just change the font to symbol. And then I get my Greek letter. It makes your Excel sheets look fancier. You can insert symbols. I can't remember how. It must be under insert. Yeah, you can insert a symbol. So if I wanted a symbol, sigma, I could still do it that way. But anyway, we're going to lose the point of why we're doing this. We want the population standard deviation of that data set using Excel. It's STDEV dot P because it's a population now. Oh, when it starts suggesting these things, you can select them, but if you hit enter on them, it does that. The secret to that is to hit tab. I don't know, it took me like 5 years to figure that out. And then it allows you to enter the values. So I could go in, this time maybe I'll highlight them. And now we get the 2.8 that we had before. And then I have my label here. And remember, in the first lab, you learned how to copy things, so might as well just copy that down rather than type it. Another thing we could do is mess around with these decimal places. Somewhere up here on the home screen, there's a decrease and increase, to make it look all pretty. Something like that. I also like to, put boxes around everything. That's under, by your bold, italics and stuff, there's borders, and there's something called all borders, and you can, make it look like a, nice grid like that. That way they'll print. Like all these gray borders don't print. I'd probably put borders around this. I'd probably center all that stuff, something like that. I'd probably give this a better title than X, children, ages of Paul's children. And you notice that it didn't fit in there very well. A cool thing you can do is you can right click on that cell and format it and alignment tab here, and you can wrap the text so that it doesn't try to, it'll allow it to go to more than one line like that. And that looks pretty cool. Maybe make my title bold. Just showing you some Excel tricks. The tutorials don't really show you all those things, so it's nice to see them in action. And another thing, when you're doing other, other projects and such, I did this on page 1. This little plus sign here lets me add another page. So if I wanted to do another example for it, I could just do it here, say. But if there's space, certainly you can just scroll down and do it below. So yeah, there's the Excel version of this. Maybe I should have hit save at some point. Yeah, save as. Just throw it on my desktop. What is this, video 3? Unit 1, video 3, Excel. Example. And now we have that. So yeah, I kind of went off the script here a little bit, but it was kind of fun to demo that. So now you know 3 ways of calculating mean and standard deviation. You can do it by hand, you can do it with your calculator, and now you can do it with Excel. And during tests and quizzes and things, you're welcome to use Excel. You're welcome to use your calculator. So any of those methods work for me. So yeah, let's go on. Remember in the previous lecture, we were talking about 2x4s and the number of defects per 50 boards. That's what this data was. Supplier B had 21 defects in 50 2x4s, and then they had 72 defects in 50 2x4s, etc. There are 20 values here, and we decided that we liked supplier B over supplier A. I decided to calculate the mean and standard deviation sort of by hand, but you can see that this is really an Excel sheet. I calculated the mean first. So first I found the sum, and then I calculated the mean from that. Actually, I probably just used the mean formula, which was average. And then this value that's up here, maybe I should put an arrow here, that value is 21 minus the mean, which is 43.1. And I had to do that for all of them. But I could just type the formula in this one cell and then copy the formula down. For this cell here, I'm just squaring that. And then I copy the formula down. And then I have to add all those up. Remember, the standard deviation is x minus x bar squared over n minus 1. Remember, this is sample data because this isn't all the possible boards that supplier B is ever going to have. So in this rather crude calculation here, basically I found this sum right here, which is 3569.8, and then divided it by n minus 1, so 20. There are 20 values here. And that's where we get 13.7 boards, or defects per 50 boards. Which is probably smaller than the standard deviation for supplier A. Go ahead and calculate that. Notice I did this a very long way. Like we learned that we could just do this with one simple formula in Excel. Start with all formulas in Excel start with that equal sign. So I could have just done equals STDEV dot S because it's a sample, and then put my data in here. Whatever column that is, B2 to B22, for example. I don't know where it is on the sheet. And for the mean, I could have, instead of doing all this work, I could have just done equals average. Excel isn't case sensitive, so if you use upper or lowercase letters in your functions, it doesn't matter. And we do the same data range. And we wouldn't have to build this whole table. I was just trying to show basically how to do it by hand again. I don't normally do an Excel demonstration there, but I thought this would be fun. The question is this a good number, a bad number, a big number, a small number? Is 13.7 a big standard deviation? And the answer is, it depends. It depends on what the mean is. You never talk about the standard deviation without talking about the mean first. The standard deviation is the average distance that any of these points are from their mean. On average, these points are 13.7 units away from 43. So 13.7 is a relatively large number compared to 43. And I can see that because I have the mean there. You would never just report the standard deviation for a data set without first saying what the mean was. So the standard deviation by itself is meaningless. 13.7 for a standard deviation is really small if your mean is 50,000. But it's kind of large if your mean is 43. So we'll work on number sense so that standard deviation can have more meaning to us. Before we do that, we should talk about a couple of other measures of variation. One of them is the variance. It's just the standard deviation squared. It's used a lot in more theoretical applications. We use variance in theoretical statistics, but we tend to use standard deviation more in applied statistics. So you probably won't run across this one that often, but I just wanted to show you. It's just the standard deviation that we had up above, but it's squared. So it gets rid of the square root. There are theoretical reasons why we would prefer to work with this in theoretical situations, but we'll mostly deal with standard deviation, primarily because this thing messes up the units. The units of standard deviation are the units of the data. Same with the mean. But when you don't take the square root, you end up with squared units, and I made a really bad, I can't even call it a joke here. If you have data that's money and you calculate the standard deviation and get a standard deviation of $7, the variance is then 49 square dollars, and it was like squaring a dollar. I don't know. It's just all the more reason not to talk about variance that much in this course, because this course is very applied, not so theoretical. One of the things about this course that's nice is the stuff that you learn in it isn't just a bridge or a stepping stone to get up to a higher stats course. A lot of these topics are used by statisticians every day. So it's nice that it allows you to get the terminology and the language so that you could discuss with statisticians in the future. You don't necessarily have to do this stuff yourself. Like when you're some big boss of some large construction company or something, you'd probably hire someone to consult with to do your statistics for you, but you'll have the ability to communicate better with them by having done some of this yourself. So coefficient of variation is the next one. This one is useful, but I don't see it used that often. Maybe in very mathy statistical journals, I will see coefficient of variation, But in general, it's not used that often. But I want you to know about it because it's exactly what I said earlier. You should never talk about the standard deviation without talking about the mean. So why not put the two together? Let's look at the ratio of standard deviation to the mean. If it's a sample, we'll do S divided by X bar. If it's a population, we'll do sigma divided by mu. And usually we multiply those by 100 and list CV as a percentage. So this is then sort of a relative variance relative to the mean. It's really nice in that one, it's easy to calculate. Two, it includes the mean already. Three, it doesn't have any units. You know, if our numerator has defects per 50 boards, and our denominator has defects per 50 boards, they'll cancel out. So you end up with a dimensionless statistic, which is really nice because then you can compare the variability of things that aren't even related. You know, was the variability on your midterm more or less than the variability of the number of people that became pirates in the last 20 years? I mean, those two things are completely unrelated, but I can still compare their relative variability by using CV. Here's a little example. I'm comparing laptops to graphing calculators. So I asked 20 of my students, hey, give me your laptop. I'm going to weigh it. So I weighed all 20 laptops, and on the mean weight turned out to be 6.5 pounds. And I said, hey, anybody have an old graphing calculator sitting in a drawer somewhere? And 15 students did, and they brought them in to me, and I weighed them and got a mean of 1 pound. So just summarizing, you know, laptop has a mean of 6.5 pounds, and the calculator has a mean of 1 pound. The standard deviation of these is also given in there. Like, imagine I have the 20 values, I punch them into my calculator, I hit my mean button, I hit my standard deviation button, and it gives me these two results. The standard deviation of the laptops is 0.1 pounds. LBS is the abbreviation for pounds. I don't know why. The standard deviation of the calculators also happens to be 0.1 pounds. So they have the same standard deviation. A layperson might say, well, they're both spread out the same. But that is not true, because 0.1 relative to 6.5 pounds isn't as big a deal as 0.1 pounds relative to 1 pound. And I did the calculations here. I did the ratios. The relative variability of the laptops is 1.54%, whereas the relative variability of the calculators ends up being 10%, which is surprising to me, as there's probably way more variation in laptops than there are in graphing calculators. So I probably made up this data. But anyway, that's kind of the gist of coefficient of variation. It's really nice for doing comparisons, particularly if your units don't match. Then it's great. In this case, this was kind of a boring example because you could tell. You could just look at this and go, wow, they have the same standard deviation and their means are so different. But had these numbers been all closer together, this would have been a tougher call. If the calculators had weighed 6.4 pounds and the standard deviation had been 0.13 or something, then we might have a harder decision to make. Continuing on, trying to understand standard deviation. This is getting kind of long-winded. Hang in there. We get this thing called the empirical rule. It's based on the bell curve. So a lot of data sets tend to follow this bell-shaped distribution where most of your data is near the mean, and then there isn't much data far above the mean or far below the mean. It turns out when it's a perfect theoretical bell curve, like the formula, I believe you had a lab where you may have, you plotted this curve. The area beneath this curve is basically how much data is in a range. In calculus, you would integrate this curve to find these percentages. In here, you'll just have to take my word for it. Looking at this thing, I'll zoom in a little bit. The mean is in the middle, as we would guess on a normal distribution. And if we take the mean and go one standard deviation above it, the mean plus sigma, or go one standard deviation below it, we get this range of values, and this area beneath the curve accounts for 68% of all of the area beneath the curve. And you could use calculus to determine that, but you'll just trust me here. If you go 2 standard deviations above the mean and 2 standard deviations below the mean, you'll see that I'm shading almost the whole thing. I'm shading 95% of the area. Once you get out to 3 standard deviations, well, I'm stopping here now. I basically get everything. This curve is asymptotic. It doesn't actually touch the axis there. It just keeps going, getting closer and closer to it. But once you get to this point, you have 99.7% of the data. Like, there isn't much out here anymore. There's only a 0.3% chance of having a value way above or way below. So typically I ask students to memorize these 3 numbers. Or in your case, write those 3 numbers on a Post-it note and stick it on your computer monitor so that you always have them, because we'll use those a fair bit, at least at the beginning of the course. So this is a way for us to use standard deviation and the mean, now that we have those terms. Now, this empirical rule only applies, these percentages only apply when you have this perfect theoretical bell curve. And sometimes your data doesn't exactly follow that. But if it roughly looks like a bell curve, then these percentages are a good ballpark. If you don't have a bell curve, or you don't know what you have at all, then you have to go a little more theoretical. There's this guy named Chebyshev. I think if you Google him, there are various spellings of his name. I think it uses Russian Cyrillic characters or something. So I don't think sometimes it doesn't always start with a CH. But anyway, not that you're all going to go and Google Chevy. His theorem is kind of complicated sounding. The fraction of a population occurring within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is greater than 1. Clearly, that is not obvious. That's a hard theorem to swallow, I think, at first. What is this? It's supposed to be related to the empirical rule, but it applies to, maybe I don't need a y-axis there. It applies to any shape. So somewhere on this thing is the mean. And then Chebyshev wants to estimate the area underneath the curve within k standard deviations. So say I pick a spot here and here, the mean plus 2 standard deviations and the mean minus 2 standard deviations. The area within that range is what Chebyshev was trying to analyze. Now, I should be a little more careful here. The curve couldn't possibly be going up at the end. It has to be approaching the axis. Oh no, I lost the whole thing. There we go. Anyway, you get the idea. In this case, what is k in this formula? It's the 2. Up above, in the empirical rule, when we're within 2 standard deviations of the mean, we get 95% of the data. Is this percentage here 95%? It may not be, right? It's harder to judge when you have a different shape. But Chebyshev has a formula that gives us this percentage, and it's just 1 minus 1 over k squared, which is pretty cool. I did those calculations on the next page. So I did what happens when k is 2. Plug 2 into the Chebyshev formula, and you get 0.75. So Chebyshev is saying that the picture I drew here, that this area isn't 95 necessarily. It's getting calculated to be 0.75 or 75%. But you'll notice that there's something weird about the formula. He doesn't tell us the exact amount. He just gives us a lower bound. It's at least 75%. So we don't know what this percentage is, but it's 75% or more. Again, I can plug in a different value for k. For the empirical rule, I know that when I'm 3 standard deviations away, I have almost everything. It's 99.7%. Chebyshev doesn't say that. He just says it's at least 89%. So Chebyshev is nice because it works for everything, but it's also bad because it's kind of general. It's so general that you don't know. At least 89 means it could be 90, it could be 95, it could be 99. So it's a nice theorem for setting at least a lower bound. Here's basically the same picture demonstrating that. I just drew a sort of random curve here, and I went with the mean was at this spot, and then 2 standard deviations above, 2 standard deviations below, and that was where we calculated the at least 75. And if you go to 3 standard deviations on either side, it's at least 88.89 or 89%. So that's Chebyshev's theorem. The downside of Chebyshev's theorem is you don't have symmetry. I can't say that above the mean is 50% and below the mean is 50%, like I can with the empirical rule. Like, I'll just quickly run back there for a second. Like, I can take advantage of symmetry here. Suppose I wanted to just know this area. Well, if I know that 68% is within 1 standard deviation, then this region between the mean and 1 standard deviation above, this is 68% divided by 2 because it's symmetric. The area right here equals the area over here, so that I know that that's 34%. So the empirical rule is nice for that, where you cannot necessarily do that if you're talking about a distribution that you either don't know or you know that is something weird. I think that's where we'll call it for this one. It got kind of long-winded, I'm sure. We'll move on to measures of position next time. Hope you enjoyed this, and I will see you in the next one. Take care.